The ground beneath your feet is constantly moving. It is part of a planetary recycling system that has been running for over 4 billion years. By the end of this, you will understand the hidden forces that build mountains and reshape continents. How did our planet develop this incredible process, and what clues are locked inside the oldest rocks on Earth? What does it mean to live on a world that continuously rebuilds itself from the inside out? That first crust was a dead end. For millions of years, our young planet simply accumulated this thin, brittle shell, only to have it shattered by incoming space rocks and swallowed back into the molten chaos below. There was no grand design, no system. It was a world of constant construction and demolition without any blueprint. But deep within that fiery ball, change was brewing. The immense heat left over from Earth's violent birth, combined with the steady warmth from decaying radioactive elements, began to stir the planet's interior. Think of a pot of soup on a very, very low simmer. The heat from the bottom causes the liquid to rise, cool at the surface, and then sink back down, creating a slow, endless circular motion. That is convection. On a planetary scale, this process is unimaginably powerful and incredibly slow. These nascent currents were the first faint heartbeat of a recycling system, but the planet was still far too hot for it to take hold. The rock needed to cool and strengthen to form a stable, rigid outer layer that could be moved by the forces beneath it. This threshold, the moment the Earth developed a strong enough lithosphere, was the turning point. So where do we find the evidence for this profound transition? The answer lies in the only witnesses that survive from that ancient era, the oldest rocks on Earth. To find these ancient witnesses, we must travel to some of the most remote and rugged landscapes on Earth. In the frigid expanses of northern Canada, the Acasta gneiss endures, a formation of rock that is over 4 billion years old. In Greenland, the Isua Greenstone Belt tells a similar story, but when you look at these rocks, you are not seeing the original skin of the planet. You are looking at something that has been profoundly changed. These are metamorphic rocks, which means they have been subjected to immense heat and pressure, cooked and squeezed until their very structure transformed. Their existence is the first great clue. If they were the first crust, they would be different, more pristine. Instead, they are evidence of recycling, proving that the truly primordial crust was destroyed, taken back into the furnace to be reborn into something new. This is why rocks from our planet's first 500 million years, the Hadean eon, are almost non-existent. They were relentlessly reworked and consumed. Geologists face what they call the missing crust problem. Where did it all go? The answer is not that it was blasted into space. It was swallowed. These ancient stones are the sole survivors of that destructive dawn, pointing directly to a process that began pulling crust back into the depths. This fundamental process is the engine of the entire system, and it all begins with a simple, powerful act of planetary physics. This grand recycling system required a mechanism, a planetary engine. That engine was revealed to us through the theory of plate tectonics, a revolutionary idea that finally explained the moving ground beneath our feet. Picture the Earth's outer shell not as one solid piece, but as a broken eggshell fractured into gigantic, interlocking plates of rock. These plates are immense rafts floating on a hotter, softer layer of the planet's interior. They are in constant, slow motion, and it is at their edges where the planet's most dramatic transformations occur. This was the key that unlocked the mystery. For the first time, geologists had a single framework that could explain why earthquakes shake certain regions, why volcanoes erupt in long chains, and how entire mountain ranges are thrust skyward. The slow-motion collision of two plates, for instance, creates immense pressure that can only be relieved by crumpling the land, forging peaks like the Himalayas over millions of years. This theory provided the how for the stone recycling process. It describes a global conveyor belt where old, dense crust is pulled down into the mantle at certain boundaries, making room for new, molten rock to rise and solidify elsewhere. The acceptance of this idea in the 1960s was a true scientific revolution. It transformed our view of Earth from a static, unchanging globe to a vibrant, dynamic world, constantly remaking itself. Now that we understand this engine, we can look directly at the specific, powerful places where this recycling is most evident. These collisions are the planet's primary recycling centers, where the slow-motion demolition of the old makes way for the new. When two plates meet head-on, a geological showdown begins, and the outcome depends entirely on their nature. The most dramatic of these encounters happens when a dense, heavy oceanic plate slams into a lighter, buoyant continental plate. The oceanic plate does not have the strength to stand its ground. Instead, it is forced downward, bending and plunging into the hot, malleable mantle below. This is the process of subduction, the cornerstone of planetary recycling. Think of it as a colossal, slow-moving conveyor belt descending directly into the Earth's furnace. This descending slab carries with it everything that settled on the old ocean floor, including vast amounts of water locked within the minerals of the rock itself. That water becomes a critical ingredient, drastically lowering the melting point of the surrounding mantle rock. This newly molten rock, now lighter than its surroundings, begins a slow ascent. It migrates upward, eventually punching through the overlying continental crust to create a line of violent and magnificent volcanoes. This is the origin of iconic mountain ranges like the Andes in South America or the Cascades in North America. Those volcanic peaks are not random. They are the direct, fiery signature of a slab of ocean floor being consumed dozens of miles below. The descent is not a smooth one. As the plate grinds its way downward, immense friction and pressure build up, releasing its energy in the form of powerful, deep-focus earthquakes that shake the land above. This entire system, from the deep trench where the plate begins its dive to the volcanic arc it creates on the surface, forms a single, interconnected recycling plant. It is here that old, cold lithosphere is returned to the mantle to be remelted, its material eventually destined to rise again as new igneous rock. This cycle does more than just reshape the continents. It also plays a surprisingly vital role in regulating our planet's climate over millions of years. The very rock that is pulled down carries with it ancient carbon, effectively scrubbing it from the atmosphere and locking it away deep within the Earth. But what happens to that slab of stone once it vanishes from our sight, embarking on its long journey back into the planet's interior? So where does that conveyor belt ultimately lead? The journey of a subducted slab is one of the most epic voyages on our planet, a descent into a realm we can only see through indirect means. A tectonic plate does not simply vanish into the abyss. Once it slips beneath the trench, it begins a multi-million-year pilgrimage into the Earth's deep interior. To track its path, scientists use a remarkable tool called seismic tomography. Think of it as a planetary CT scan. Just as medical imaging uses X-rays to map the inside of a human body, seismologists use the energy waves from earthquakes to create three-dimensional images of our planet's internal structure. These waves travel at different speeds through materials of varying temperatures and densities. By analyzing thousands of earthquakes from all over the globe, they can map where cold, dense slabs are sinking through the hot, softer mantle. What these images reveal is a complex and layered journey. Many slabs seem to meet a significant obstacle about 660 kilometers down, at the boundary between the upper and lower mantle. Here, they often flatten and stagnate, piling up like immense, slow-moving traffic jams in the planet's interior. The incredible pressure and change in mineral structure at this depth can act as a temporary barrier, causing the descending rock to accumulate for eons before it potentially finds a way to continue its descent. Some slabs, however, are dense enough to power through this boundary. Their journey may take them all the way to the very bottom of the mantle, to a mysterious region resting directly on the Earth's molten outer core. This zone, known to scientists as the D double prime layer, is one of the most enigmatic places inside our world. It is here that these slabs of ancient ocean floor may finally come to rest, accumulating in vast underground graveyards. They are not instantly blended back into the mantle. Instead, they can remain as distinct chemical reservoirs, storing the material of continents and oceans that existed billions of years ago. This discovery fundamentally changes our view of the mantle. It is not a perfectly mixed blender, but a place with a deep, layered history, preserving the remains of our planet's most ancient crust. But if this material is simply sinking down and piling up, how does the cycle ever complete itself? How does this ancient stone ever find its way back to the surface? The journey down is only half the story. Deep within the mantle, the heat from the Earth's core begins to work on those sunken slabs. In the planet's deepest reaches, immense temperatures can cause these ancient graveyards of rock to become unstable. Pockets of material begin to heat up, becoming less dense than their surroundings. Slowly, over millions of years, this buoyant rock begins to rise, forming colossal pillars of hot material known as mantle plumes. These are not part of the plate tectonic conveyor belt, but something far more profound, massive upwellings from the very base of the mantle. Think of a lava lamp with a great blob of warm wax detaching from the bottom and slowly rising to the top. On a planetary scale, this process creates a powerful thermal current that can punch straight through the overlying plates. When one of these plumes reaches the surface, the results are spectacular. It can flood an area the size of a continent with lava, creating vast volcanic plateaus, or it can burn a sustained hole in a moving plate, generating a chain of islands. This is the secret behind the Hawaiian island chain. The Pacific plate is slowly drifting northwest, while a stationary mantle plume burns a fixed spot beneath it. As the plate moves, the plume creates a new volcano, leaving a trail of extinct islands in its wake. The big island of Hawaii is currently positioned over this hotspot, and a new island named Loihai is already growing on the seafloor, destined to become the next member of the archipelago. But the real proof of the recycling process lies in the lava itself. When scientists analyze the chemical composition of the rock erupted at Hawaii and other hotspots, they find a telling signature. The lava contains certain isotopic traces that are characteristic of material that was once at the surface, material that was processed through water and life. This is the ultimate evidence. It proves that the molten rock fueling these majestic volcanoes contains within it the recycled remains of ancient ocean floor, crust that was pulled down by subduction hundreds of millions of years ago and has now completed its epic round trip. This is the planet's great act of renewal, creating new land from the literal ashes of the old. This upward journey of mantle plumes works in perfect partnership with the downward pull of subduction, forming a complete closed-loop system. Yet there is another essential part of this planetary machine, one that creates the space needed for all this new rock to emerge. Far below the churning waves of the ocean, the planet operates its most prolific construction site. Here, along a vast, submerged mountain range that wraps around the entire globe, the Earth is literally tearing itself apart. This is a divergent boundary where two tectonic plates are slowly, inexorably pulling away from each other. As they separate, a deep rift valley is carved into the seafloor, creating a gaping wound in the planet's crust. But nature abhors a vacuum, and into this void rises the hot, plastic rock of the underlying mantle. This ascent is the key to the entire process. As the solid mantle rock rises, the immense pressure confining it drops dramatically. This release of pressure, a phenomenon known as decompression melting, causes the rock to partially melt even though its temperature hasn't increased. It is like uncorking a shaken bottle of soda. The sudden drop in pressure allows dissolved gases to come out of solution. In this case, it is molten rock that is liberated. This magma, being less dense than the surrounding solid material, migrates upward to fill the fissures, cooling and solidifying to form a continuous sheet of new basaltic crust. This is the planet's primary crust-forming factory, a 60,000-kilometer-long volcanic chain that is constantly adding new real estate to the ocean floor. It is a place of pure creation where the very ground we walk on is born. Yet, the source of this new land holds a deeper secret. The mantle from which this magma rises is not a pristine, primordial reservoir. It is a colossal, slow-moving mixture of material, a blend of rock that has never seen the surface and fragments of ancient crust that were drawn down by subduction and have been stirred back into the convective cycle. Therefore, even the new crust being forged at these ridges is, in a very real sense, made from recycled stone. The process acts like a planetary smelter, taking raw materials from the mantle, some virgin and some recycled, and forging them into a new product, fresh oceanic crust. This newly formed crust then begins a slow, inevitable journey. It is carried away from the ridge by the conveyor belt of plate motion, cooling, thickening, and accumulating a blanket of sediment as it travels across the ocean basin. Its ultimate destination is almost always a collision, a fate sealed millions of years earlier at its birth, destined for a subduction zone where the cycle will begin anew. The perfect symmetry is breathtaking, creation and destruction operating in a balanced planetary dance. But how can we be so certain of this grand, slow-motion cycle? The proof is not just in the theory, it is written in the very stone beneath our feet, a magnetic memory locked into the ocean floor. The same planetary recycling that moves continents also works on a microscopic scale in the life of every single stone. This is the rock cycle, a continuous loop of destruction and creation that operates within the grand framework of plate tectonics. It begins deep underground with igneous rock, the foundation of all crust, forged from the cooling of molten magma. But no rock is permanent at the surface. Exposed to wind, rain, and ice, it begins to crumble, slowly broken down into tiny fragments. These particles, the sediments of erosion, are carried away by rivers and streams, eventually settling in layers at the bottom of lakes and oceans. Over immense stretches of time, these layers are buried under more and more sediment. The weight above creates immense pressure, squeezing the particles together, and mineral-rich water cements them into a new form, sedimentary rock. Think of a layer of mud and sand on an ancient seafloor, slowly transforming into solid shale or sandstone. This is just one stage in the journey. If this new rock is then dragged down at a subduction zone or buried deep by a mountain-building collision, it encounters the planet's interior heat and crushing pressure. These forces cook and contort the rock, changing its very crystal structure without melting it outright, transforming it into a metamorphic rock like slate or schist. And if the heat becomes intense enough, if the rock is pulled far enough down into the mantle, it will melt completely, its identity erased as it returns to the state of magma, ready to cool and crystallize once more as a new igneous rock. A single grain of sand on a beach today could have been part of a granite mountain 200 million years ago, then a layer of mud at the bottom of a vanished sea, and a sparkling crystal in a mass of metamorphic gneiss, all in a single epic existence. This intimate cycle reveals that planetary recycling is not some distant abstraction. It is the fundamental life story of the ground we walk on. But to truly grasp the timescale of this endless transformation, we need a reliable clock, a way to measure the deep time inscribed in the stone itself. A single stone can hold multiple birthdays, each one marking a different chapter in its epic life. To read this deep history, geologists use a tool more precise than any calendar, a clock that ticks to the rhythm of atomic decay. The key lies in radioactive isotopes, unstable forms of elements trapped within minerals when they first crystallize from cooling magma. From that moment, they begin a steady, irreversible transformation, decaying at a known and unchangeable rate into different, stable elements known as daughter products. By carefully measuring the ratio of the remaining parent isotope to the accumulated daughter product in a rock sample, scientists can calculate exactly how long ago those minerals first formed. This gives us the rock's crystallization age, the moment it was born from the planet's fiery interior. But what happens when that rock is swept back into the planetary mill? If it is buried deep and heated during a mountain-building event, the intense temperatures can act like a reset button. The crystal structure is shaken up, allowing the accumulated daughter isotopes to escape, effectively setting the atomic clock back to zero. When the rock cools again, the clock starts ticking once more. This gives the very same stone a second, younger age, known as its metamorphic age. So one piece of gneiss might tell us it first crystallized from magma 2.8 billion years ago, but was then completely transformed by heat and pressure 1.8 billion years ago. It carries two distinct dates in its crystalline structure, a direct record of its long journey. These isotopic systems are the ultimate forensic tools, allowing us to reconstruct the biography of a stone as it passed through the tectonic mill. The evidence gathered from countless such rocks points to a startling and profound fact. The planet's recycling rate is not constant. It has pulsed and slowed over billions of years, a rhythm dictated by the Earth's internal heat engine. The rhythm of our planet's great recycling machine is not a steady, monotonous beat. It is a symphony of geological pulses, with movements of frantic activity followed by stretches of profound quiet. Evidence locked in ancient rocks reveals a history of tectonic surges, periods where mountain building accelerated and the grinding together of continents reached a crescendo. This cyclical drama is written in the Supercontinent Cycle. Think of the assembly of a supercontinent like the last great one, Pangaea. This was not a gentle coming together. It was a colossal traffic jam of nearly all the world's landmasses, a process that required a frenzy of subduction zones to pull the oceanic plates together. All those simultaneous conveyor belts plunging into the mantle would have supercharged the recycling of oceanic crust, drawing down vast volumes of old seafloor in a relative geological instant. But such intense consolidation could not last. The planet's internal heat, trapped beneath this massive, insulating lid of continental rock, would eventually build up, triggering the supercontinent's inevitable breakup. This is when the planet's construction sites go into overdrive. As the land mass fractures, new mid-ocean ridges unzip between the separating continents, pouring forth immense quantities of fresh basaltic crust and literally pushing the newborn continents apart. This variable pace, the pulse between assembly and breakup, means the planet's recycling efficiency has never been constant. Some researchers even suggest the entire system may have begun in fits and starts. The engine of plate tectonics might have sputtered to life in isolated regions over 3 billion years ago, only later becoming the seamless, global conveyor belt we see today. This changing tempo of destruction and creation did not just reshape the continents, it fundamentally altered the entire surface of the world. The rate at which carbon was pulled from the atmosphere and buried in the deep earth through subduction would have fluctuated wildly. Intense volcanic activity during breakups could have poured carbon dioxide back into the air, warming the planet, while the rapid erosion of giant mountain ranges during assemblies could have drawn down carbon dioxide, cooling the globe. These tectonic pulses, operating over hundreds of millions of years, set the stage for the evolution of life, opening and closing seaways, creating and destroying habitats, and directly influencing the very air that organisms breathe. To understand the deep past and the long-term future of our world, we must learn to listen to this slow, powerful rhythm of stone. This geological thermostat has been operating for billions of years, a silent partnership between the shifting ground and the sky above. The engine of this climate control is the element carbon, and its journey is masterfully orchestrated by plate tectonics. On one hand, our planet's volcanoes are constantly venting carbon dioxide into the atmosphere. This happens not only at the dramatic, cone-shaped volcanoes of subduction zones, but also all along the vast, hidden mid-ocean ridges where new seafloor is born. If this were the only process at work, Earth would have overheated eons ago, becoming a scorching Venus-like world. But a powerful counterbalance is always at work, a process that acts as the planet's air conditioner. When tectonic collisions thrust up massive mountain ranges like the Himalayas, they expose vast quantities of fresh, silicate rock to the open air. Rain, which is naturally slightly acidic, falls on these new mountains and begins to chemically break down the rock in a process called weathering. This chemical reaction pulls carbon dioxide directly out of the atmosphere, incorporating it into dissolved minerals that are then washed down rivers and into the sea. There, tiny marine organisms use these minerals to build their shells, and when they die, those shells sink to form thick layers of limestone and other carbonate rocks on the ocean floor. This is how carbon is literally turned to stone, but the cycle does not end there. The relentless march of the plates ensures that these ocean floors, laden with their captured carbon, are eventually pulled back into the mantle at subduction zones. Some of this carbon is cooked out of the descending slab and recycled right back into the atmosphere through volcanic eruptions, ready to begin the cycle again. Another portion, however, is carried deep into the Earth, stored away for millions of years. This exquisitely balanced feedback loop is our planet's built-in climate stabilizer. When CO2 levels and temperatures rise, weathering rates tend to increase, pulling more greenhouse gas out of the air. When the planet cools, weathering slows, allowing volcanic CO2 to gradually rebuild the atmospheric blanket. This dance between the living rock and the atmosphere is the primary reason Earth has remained habitable for so long, avoiding the fate of a permanent icehouse or a runaway greenhouse. This life-sustaining environment, forged by the recycling of stone, may have also provided the very stage for life's first act. The same tectonic forces that regulate our climate also created the complex, nutrient-rich environments where the first fragile organic molecules could have assembled and thrived. Could the very first stirrings of life have been a product of this planetary recycling machine? The answer may lie in the deepest, darkest parts of our oceans, at places where the Earth's fiery interior meets the cold deep sea. These are hydrothermal vents, spectacular underwater geysers that exist solely because of the tectonic forces creating new seafloor. At mid-ocean ridges, cold seawater does not simply sit on top of the new crust. It is pulled downward, seeping through countless cracks and fractures in the hot, young rock. As it descends, it becomes superheated, sometimes reaching temperatures over 400 degrees Celsius, and it undergoes a profound chemical transformation. The scorching water leaches minerals and metals from the surrounding basalt, becoming a rich, chemical-laden fluid. Forced back up to the seafloor by its intense heat and buoyancy, this fluid erupts from towering chimneys, creating the otherworldly landscapes of black smokers, billowing clouds of dark, mineral-rich water into the eternal darkness. But there is another, more ancient kind of vent, known as an alkaline vent. These are cooler and composed of a different mineral, and they may hold an even more profound secret. They provide a sustained, non-toxic source of chemical energy and a complex array of the very building blocks necessary for life, such as amino acids and lipids. The physical structure of these vents is perhaps their most ingenious feature. Their chimneys are not solid walls, but complex, porous matrices, filled with a honeycomb of microscopic compartments. Think of these tiny pores as nature's first laboratories. Within these protected, cell-sized spaces, the rich chemical soup from the vent fluid could have been concentrated and held in place, allowing simple molecules to interact and form more complex chains, the precursors to proteins and genetic material. The vent's porous rock would have acted as a primitive scaffold, a mineral membrane that facilitated the incredibly delicate chemical reactions needed to cross the threshold from non-living chemistry to a living, self-replicating system. This means the planet's stone recycling machinery did not just create a habitable environment by chance. It may have actively constructed the first incubators, engineering the precise conditions required for life to emerge. The entire process is fueled by the relentless recycling of water itself, drawn from the ocean, driven through the hot crust, and returned, transformed to the seafloor, carrying within it the potential for everything that was to come. The very oceans that define our blue planet are also caught in this endless loop of renewal. Every drop of seawater is on a journey far more epic than any surface current, a voyage into the earth and back again. It begins at the mid-ocean ridge where fresh, hot crust is born. This new basalt is initially dry and porous, like a colossal sponge just pulled from a kiln. As it cools and travels away from the ridge, it is exposed to the immense pressure of the deep ocean. Seawater is forced into every crack and pore, but it does more than just fill empty space. It chemically reacts with the rock. Water molecules are incorporated directly into the crystal structures of minerals, transforming them into hydrated forms like serpentine. This is how the ocean floor becomes a massive, submerged reservoir, locking away unimaginable volumes of water within the stone itself. The fate of this water is sealed when the plate reaches a subduction zone. As the slab bends and begins its descent, it carries this bound water with it, pulling the ocean down into the planet's interior. The journey downward is a trial by fire and pressure. At depths of around 100 kilometers, the increasing heat and crushing force literally squeeze the water back out of the sinking rock, like wringing a wet towel. This liberated water does not simply vanish. It rises into the wedge of mantle rock directly above the subducting slab. Water has a miraculous effect on solid rock. It drastically lowers the temperature at which the mantle will melt. This flux melting, triggered by the addition of water, generates the vast chambers of magma that feed the iconic volcanoes of the Pacific Ring of Fire. In this way, the water that was once locked in the ocean floor returns to the surface, riding plumes of steam and ash in spectacular volcanic eruptions, completing its circuit. Some of the water, however, travels much deeper, bound in ultra-dense minerals that can carry it hundreds of kilometers into the lower mantle, forming vast hidden reservoirs. This deep water cycle is the silent, essential partner to the rock cycle. Without the constant recycling of water into the mantle to lubricate the process and facilitate melting, the entire engine of plate tectonics would likely stall. The grinding of plates would cease, volcanoes would fall silent, and the planet's great conveyor belt would stop. This reveals a profound truth: the Earth does not just recycle stone, it recycles oceans. The ground we stand on and the water that surrounds it are part of a single, inseparable system of renewal. We can walk directly across a vanished ocean floor. Scattered across the continents are colossal, stranded fragments of ancient oceanic crust known as ophiolites. These are not mere rocks, but entire geological cross-sections, slices of the deep sea that have been lifted high and dry by the immense power of tectonic collisions. They are our most direct windows into a world usually hidden by kilometers of dark water. In places like the spectacular Seismic ophiolite in Oman, you can traverse a complete timeline of an oceanic plate's life. Your journey begins by walking on rock that once was the Earth's upper mantle, a dense, greenish peridotite that formed the conveyor belt's foundation. As you climb, you pass through the fossilized remains of massive magma chambers, where molten rock pooled and crystallized. Higher still, you encounter the incredible sheeted dike complex, a stunning geological library where wall after wall of vertical rock reveals the countless fissures that channeled lava up to the surface. And at the very top, you find the pillowed basalts, the final product, their distinctive blob-like shapes frozen in time, exactly as they formed when hot lava met cold seawater and instantly solidified. This entire vertical sequence is a tangible, walkable museum exhibit of the seafloor's creation. But ophiolites tell an even deeper story. Geologists can examine the signs of hydrothermal alteration, seeing how seawater chemically transformed the hot rock, locking water into minerals and creating the very conditions that would one day carry that water into a subduction zone. These stranded relics are the ultimate physical proof of the conveyor belt, offering a piece of the recycled crust we can hold in our hands. Yet this revelation leads to a new and profound question. If the dense ocean floor is so readily consumed and recycled, what about the continents themselves? Are they also just temporary passengers on this slow-moving geological treadmill? Or do they play a different, more permanent role in the planet's grand design? Continents are the great survivors of our planet. While the ocean floor is constantly being remade and destroyed on a timescale of 200 million years, the continents float like permanent, buoyant corks on the dense mantle below. This remarkable longevity comes down to their fundamental composition. Oceanic crust is made of dark, heavy basalt, which is dense enough to sink back into the mantle with ease. Continental crust, however, is built from lighter rocks like granite, rich in silica and aluminum. This chemical recipe makes it inherently buoyant, stubbornly resisting the downward pull of subduction zones. When a continental plate meets an oceanic plate in a colossal tectonic collision, it is always the denser oceanic plate that loses, diving beneath the unyielding continent. The continent itself might be scarred and crumpled at its edges, pushed upward into a mighty mountain range, but its core remains, refusing to be swallowed. This is why we can find ancient stones on the surface today that are over 4 billion years old, a testament to their incredible resilience. The most enduring parts of the continents are their ancient hearts, known as cratons. These vast, stable interiors, like the Canadian Shield or the core of Australia, have remained largely undisturbed for billions of years. They are the planet's ultimate historical archives, preserving a continuous, unbroken record of Earth's early history that the fleeting oceanic crust could never hold. Yet for all their permanence, continents are not static museums. They are living, growing entities. Their edges are dynamic construction zones. At subduction boundaries, the same process that consumes oceanic crust also builds new continental crust. The magma generated by the melting slab rises to form volcanic mountain chains like the Andes, which are essentially new additions of continental rock welded onto the existing landmass. Continents also grow through a process called terrain accretion. Imagine a small island like Japan or a fragment of an ancient volcanic arc riding a tectonic plate toward a continent. When it arrives, it does not subduct. Instead, it slams into the continent and sticks, becoming a permanent, welded addition to the coastline. Over hundreds of millions of years, these collisions have sutured together the patchwork of geological provinces that form our modern continents. So while the continental cores resist total recycling, their edges are constantly being reshaped, rebuilt, and expanded. The continents we recognize on a map today are the cumulative result of this endless, slow-motion construction project, a testament to both their enduring nature and their capacity for change. This grand, rhythmic pulse of assembly and breakup is the ultimate expression of the planet's recyclable nature. The Supercontinent Cycle operates on a timescale almost too vast to comprehend, a 400 to 500 million year heartbeat that reorganizes the entire face of the world. Think of it as the planet's slowest, most majestic dance. The continents, those buoyant survivors, are not drifting aimlessly. They are drawn together over eons, pulled by the relentless traction of subduction zones that gradually close the ancient oceans between them. This is the assembly phase, a colossal tectonic convergence where continents collide and weld together along immense mountain belts, forging a single, sprawling landmass like Pangaea. But this very act of creation contains the seeds of its own destruction. A supercontinent acts as a giant, insulating blanket, trapping the Earth's internal heat beneath it. This heat cannot escape easily, and so it begins to accumulate, causing the entire continental lid to bulge and dome upward. Eventually, the strain becomes too great. The supercontinent, weakened from below, begins to tear itself apart. Vast rift valleys fracture the land, and new mid-ocean ridges surge to life, pouring fresh basalt into the widening gaps and pushing the continental fragments apart on a sea of newborn crust. This cycle of assembly and dispersal is the meta-narrative of plate tectonics. It is not merely about moving continents, but about periodically reorganizing the entire planetary surface. The consequences are profound. When all the land is gathered into one place, the interior becomes a vast, arid super-desert, far from the moisture of the sea. Ocean currents, once able to circulate freely around the globe, are blocked and rerouted, radically shifting heat distribution and plunging the planet into different climate regimes. These changes create and destroy habitats on a colossal scale, forcing life to adapt, migrate, or face extinction. The assembly of a supercontinent often correlates with mass extinctions, while its breakup opens new evolutionary pathways as populations become isolated on drifting continental fragments. This grand cycle raises a final, compelling question. Our planet learned to recycle its stone, creating a dynamic, habitable world. But did other planets develop this same magnificent system, or is Earth's restless geology a solitary phenomenon in the cosmos? Our planetary neighbors stand as silent monuments to what could have been. Mars, the red planet, is a world frozen in geological time. Its surface is scarred by immense volcanoes like Olympus Mons, the largest in the solar system, but these are relics of a bygone era. Mars is smaller than Earth, and that smaller size meant its internal fire faded much more quickly. Its heat engine sputtered and died, leaving behind a single, unbroken shell of lithosphere. Without the driving force of a churning mantle, the planet's recycling system shut down completely. Its crust became a static, unchanging landscape, its history written in ancient lava, flows, and impact craters that have remained undisturbed for billions of years. Venus, shrouded in thick clouds, presents a different and more chaotic story. It may not be entirely geologically dead, but its process is nothing like Earth's graceful cycle. Evidence suggests Venus experiences catastrophic, planet-wide resurfacing events. Instead of the steady conveyor belt of plate tectonics, immense heat builds up beneath its thick lithosphere until the pressure becomes unbearable. The entire surface then cracks and founders in a global volcanic apocalypse, flooding the planet with lava and wiping the geological slate clean. This is a cycle of violent, episodic overturn, not the continuous, organized recycling that defines our world. So why is Earth the master recycler? It comes down to a perfect and perhaps precarious combination of factors. Our planet is the right size, large enough to retain the immense internal heat needed to power the mantle's convection for billions of years. Its composition provides the right mix of radioactive elements to keep that engine stoked. And crucially, it has water. Water acts as a lubricant in the subduction zones, weakening the rocks and allowing plates to slide and sink. It also drastically lowers the melting point of the mantle rock, fueling the volcanoes that build new continents. This delicate balance of size, heat, and water creates the only known continuous, self-sustaining plate tectonic system in our solar system. This is not a minor geological detail. It is the fundamental reason Earth is a living, breathing world, and not a static museum piece like Mars or a pressure cooker like Venus. Our planet's unique ability to recycle its stone is what created the stable, dynamic environment where life could not only emerge, but thrive for eons. Life itself became a geological force, a silent partner in the planet's great work of renewal. For billions of years, the most powerful agents of rock recycling were not just ice and rain, but trillions of unseen microbes. These tiny organisms colonized the bare stone of the early continents, secreting acids and other chemicals that slowly, relentlessly, broke the rock apart from the inside out. They turned barren rock into fertile soil, accelerating the weathering process far beyond what water and wind could accomplish alone. This was the first biogeochemical partnership where biology and geology began to dance. Then life evolved a new and powerful tool. When plants conquered the land, they did not simply live on the rock, they actively attacked it. Vast root systems acted like natural chisels, physically prying apart cracks and fissures. As roots respired, they released carbon dioxide directly into the soil, creating a weak carbonic acid that dissolved crucial minerals like calcium and magnesium. This biological weathering became a turbocharged version of the planetary thermostat. By pulling carbon dioxide out of the atmosphere at an accelerated rate, life began to exert a direct and powerful influence on the global climate, cooling the planet and deepening the very cycle that made its existence possible. But life's role did not end on land. In the sunlit surface waters of the oceans, a different kind of carbon capture was underway. Countless tiny marine organisms, from microscopic plankton to coral polyps, began pulling dissolved minerals from the seawater to build their shells and skeletons. When these creatures died, their calcium carbonate remains drifted down through the dark water, accumulating in thick, white layers on the seafloor. Over millions of years, these layers of biological debris were compressed into immense formations of limestone and chalk. Think of the white cliffs of Dover. Those stunning coastal walls are not made of stone born from fire, but from the compacted skeletons of ancient sea life. This represents a monumental transfer of carbon from the ocean and atmosphere into the solid rock of the planet itself. And this entire process was made possible by the tectonic machinery that created the shallow, stable marine basins where these organisms could thrive in the first place. Life did not just adapt to the world geology provided, it began to actively maintain it, weaving itself into the very fabric of the planet's recycling system. The ground we walk on and the air we breathe are testaments to this enduring partnership between the living and the stone. The same geological forces that build mountains also forge the very foundations of our modern world. The planet's relentless recycling machinery is the ultimate alchemist, concentrating scattered atoms into the rich metal deposits that power our civilization. At the deep trenches where oceanic plates plunge into the mantle, a hidden refining process begins. As the sinking slab is squeezed by immense pressure, it releases superheated water that is anything but pure. This fluid, rich in dissolved salts and gases, becomes a potent chemical solvent. It leaches metals like copper, gold, and molybdenum from the vast volume of surrounding rock, creating a concentrated, mineral-rich brine. This metallic soup then migrates upward, following cracks and fissures toward the surface. When it encounters cooler conditions or reacts with different rock types, the metals abruptly fall out of solution, much like sugar crystallizing from supersaturated syrup. They accumulate in veins and dispersed pockets, forming the giant porphyry copper deposits that are the backbone of the global electrical and construction industries. The great copper belts of South America, from Chile to Peru, are direct products of this subduction zone refining process, their wealth literally distilled from the planet's interior. Meanwhile, at the other end of the cycle, the undersea construction sites at mid-ocean ridges are also metal factories. There, cold seawater circulates through the fractured, hot rock of the new crust, becoming a black, superheated fluid charged with dissolved metals like copper, zinc, and silver. When this fluid erupts back into the icy ocean water, the metals instantly precipitate, building towering chimneys and sprawling fields of massive sulfide deposits on the seafloor. These are the raw, submarine equivalents of the mines we dig on land. Even the most coveted gemstone is a child of this cycle. A diamond begins its life as simple carbon, perhaps from the remains of ancient sea life settled on an ocean floor. When that seafloor is dragged down into the mantle at a subduction zone, the carbon is carried to depths of over 150 kilometers. There, under crushing pressure and scorching heat, the carbon atoms are forced into an incredibly tight, rigid crystal lattice. These diamonds remain trapped in the deep mantle for eons, until they are violently blasted toward the surface by a rare and powerful volcanic eruption known as a kimberlite pipe. This eruption travels upward at astonishing speed, ripping a path through over 100 kilometers of solid rock to deliver its sparkling cargo to the surface. From the copper in the wires of our homes to the gold in a wedding band and the diamond in an engagement ring, we are building our societies and marking our most important moments with gifts from Earth's deep, self-renewing furnace. Our planet hums with a deep, resonant frequency. To hear this geological heartbeat, scientists have placed a stethoscope on the Earth itself, a global network of incredibly sensitive seismometers. Each time the ground shakes from an earthquake, it sends out waves of energy that radiate through the planet's interior. These waves are not all the same. Some travel through the body of the Earth while others ripple across the surface, and each type reacts differently to the material it encounters. A seismic wave will slow down when passing through hot, partially molten rock, and speed up when moving through a cold, dense slab. By collecting data from thousands of these events all over the world, supercomputers can assemble the information into a stunning three-dimensional map of the Earth's interior. This technique, known as seismic tomography, lets us watch the recycling process in real time. we can trace the descent of a cold tectonic plate as it sinks into the mantle, seeing it flatten and stagnate at certain depths or power all the way down to the core. We can visualize the slow, powerful ascent of a mantle plume from the deepest reaches, a great column of hot rock rising to fuel a volcanic hotspot. This is no longer just a theory, it is a moving picture of our planet's inner workings. From the surface, another fleet of eyes watches the constant motion. A constellation of satellites equipped with GPS receivers measures the imperceptibly slow drift of the continents with astonishing precision. They can detect the North American plate moving away from Europe at about the same speed your fingernails grow. They see the build-up of strain along a fault line as two plates lock together, storing energy that will one day be released in a violent earthquake. These satellites also measure tiny changes in the Earth's gravitational field. Because gravity is slightly stronger over areas of dense rock and weaker over less dense regions, these measurements can reveal the immense, sinking weight of a subducting plate or the deep, buoyant root of a mountain range pushing down into the mantle. Together, these technologies have transformed our understanding. We are no longer just reading the history of the Earth from ancient stones. We are witnessing its dynamic present, watching the great conveyor belt of stone in motion, and listening to the steady, billion-year-old rhythm of a world that never stops rebuilding itself. A fossil compass lies hidden within the stone itself. This is the science of paleomagnetism, a field that unlocked one of the most compelling proofs of our planet's restless nature. When lava erupts onto the seafloor at a mid-ocean ridge, it is intensely hot, and within that molten rock are tiny, iron-rich minerals. As the rock cools and solidifies, these mineral grains act like countless microscopic compass needles, swinging to align with the Earth's magnetic field at that precise moment in time. They then lock into that orientation, creating a permanent, indelible record of where the planet's magnetic north was located when that piece of crust was born. Every new slab of seafloor becomes a page in a planetary diary, stamped with a magnetic date. The real revelation came when research vessels began towing magnetometers back and forth across the Atlantic Ocean. They were not expecting to find a perfect, symmetrical pattern, but the data revealed something astonishing. On either side of the mid-Atlantic ridge, the ocean floor was striped with parallel bands of rock, each band magnetized either in the same direction as today's magnetic field or in the exact opposite direction. These stripes formed a mirror image, a perfect set of magnetic twins on either side of the ridge. This was the smoking gun. The only possible explanation was that new crust was continuously forming at the ridge, recording the current magnetic field, and then being forcibly split in two, with each half moving away from the ridge like a pair of colossal, stony conveyor belts. The stripes recorded a history of the Earth's magnetic field flipping its polarity, with north and south swapping places over geological time. Each pair of matching stripes, one on the east and one on the west, represented a single, simultaneous burst of creation during a specific magnetic period. When this crust eventually reaches a subduction zone and is pulled back into the mantle, its magnetic memory is erased in the planet's furnace, its story concluded. But the symmetrical pattern on the remaining seafloor acts as an irreversible tape recording, a direct and undeniable log of the plate's motions over millions of years. This magnetic barcode proves the entire ocean floor is in motion, providing a timeline for the very recycling process we have been following. But what happens when the planetary engine finally runs out of fuel? The same internal fire that has driven this magnificent system for over 4 billion years is not an infinite resource. Deep within the Earth, the radioactive elements that provide a crucial portion of the planet's heat are steadily decaying, their output diminishing with each passing eon. They are a battery slowly draining. As the planet continues its inevitable cooling, the mantle's convection currents will begin to lose their vigor. The great conveyor belt of stone will slow. Scientific models paint a startling picture of this distant future, projecting that in another 1 to 2 billion years, the planet may cool to a point where plate tectonics grinds to a virtual halt. The continents will freeze in their places, their epic wanderings concluded. The rumble of volcanoes will fade into silence as the magma chambers beneath them cool and solidify. The deep, essential recycling of water and carbon, the very processes that have regulated our climate and nourished the continents, will slow to a crawl. This will trigger a cascade of consequences for the biosphere. The planet's geological thermostat will break. Without the constant drawdown of carbon dioxide through weathering and subduction, the atmosphere will slowly lose its ability to regulate temperature. The balancing act that has kept Earth habitable for so long will be thrown into disarray, potentially leading to extreme temperature swings. Life, which has so intricately woven itself into this geological dance, would face a world of profoundly different and likely harsher rules. This reveals a humbling truth. Our planet's ability to recycle itself is not a permanent feature. It is a brilliant, dynamic chapter in Earth's history with a distinct beginning and ultimately an end. The fact that we exist in this vibrant, active window of geological time, witnessing the mountains rise and the continents drift, makes our current era not just normal but remarkably special. One of the most persistent ideas is that the rock cycle and plate tectonics are identical. They are partners in a grand dance, not the same dancer. The rock cycle describes the life story of a stone, its journey from molten magma to solid igneous rock, its erosion into sediment, its compression into sedimentary layers, and its transformation under heat and pressure into a metamorphic form. It is the biography of the rock itself. Plate tectonics, however, is the colossal planetary stage upon which that biography is written. It provides the immense forces that push rocks deep underground to be metamorphosed, that lift mountains to be eroded, and that open rifts where new magma can rise. One is the intimate story of transformation. The other is the global engine that makes it possible. We often picture the mantle as a churning sea of liquid rock, but this is a simplification that obscures its true nature. The mantle is overwhelmingly solid, a vast realm of hot, dense silicate rock. Yet, under the incredible heat and pressure found hundreds of kilometers down, this solid rock loses its brittleness. It behaves like a thick, viscous fluid over immense spans of time. Think of a glass window pane in a centuries-old cathedral. If you look closely, you might see that the glass is slightly thicker at the bottom. It has flowed imperceptibly slowly under its own weight over hundreds of years. The mantle flows in a similar way, but on a scale of millions of years, its plasticity allowing the rigid plates above to glide and collide. The fate of a subducting plate is also frequently misunderstood. It is a common assumption that the descending slab of ocean floor melts immediately as it plunges into the hot mantle. The reality is far more fascinating. The slab itself remains mostly solid to astonishing depths, sometimes over 500 kilometers down. Its true power lies in the water it carries. As the plate is squeezed, this bound water is literally wrung out of the rock, rising into the wedge of mantle above it. This released water acts as a powerful flux, dramatically lowering the melting point of that surrounding mantle rock. It is this flux melting that generates the magma, not the melting of the slab itself. The descending crust is more like a water truck dampening a pile of sand to make it moldable, rather than a block of ice melting in the sun. And what of the idea that the planet learned to recycle? This was never a conscious act, but the inevitable outcome of physics and chemistry. As the young Earth cooled, it crossed a critical threshold. Its outer shell grew strong enough to be broken into plates, yet its interior remained hot enough to drive convection. Water became trapped in the crust, providing the essential lubricant for subduction to begin. Once this precise set of conditions fell into place, a self-sustaining system clicked into motion, a feedback loop of creation and destruction that has run continuously ever since. Understanding these nuances does not diminish the wonder, it deepens it. The true story is not one of sentient design, but of a beautiful, emergent order arising from the fundamental laws of our universe. Our own footprints are now etching a new layer into the planetary record. On the scale of deep time, human civilization is a fleeting moment, yet our collective actions are moving rock and soil at a staggering pace. Each year, the global activities of mining, urban construction, and intensive agriculture displace billions of tons of sediment and stone. This human-caused movement of material now genuinely rivals the natural rates of erosion carried out by all the world's rivers combined. We have become a geological force in our own right, reshaping the surface of the planet with a speed that nature typically reserves for cataclysmic events. But our most profound interference lies not in the rock we move, but in the ancient carbon we unleash. The coal, oil, and gas we burn for energy represent carbon that was slowly, patiently buried over hundreds of millions of years. Plant matter from vast swampy forests and microscopic marine life were locked away in sedimentary rocks, a key part of the planet's long-term climate regulation. We are now releasing this stored carbon back into the atmosphere in a geological instant, a span of mere centuries. This act effectively short-circuits the slow, graceful dance of the natural carbon cycle. The planetary thermostat, which relied on a delicate balance between volcanic outgassing and the slow drawdown of weathering and subduction, is being overwhelmed by a sudden, massive influx of greenhouse gases. We cannot stop the great tectonic conveyor belt. Its momentum is driven by the Earth's immense internal heat. Yet we are adding a new, incredibly rapid and disruptive pulse on top of these ancient rhythms. Our challenge is no longer just to understand this magnificent system, but to recognize our powerful role within it and learn to manage our impact with a sense of responsibility that spans generations. The planet will continue to recycle its stone long after we are gone, but the world it sustains in the meantime is now undeniably in our hands. From the chaotic formation of the first crust to the slow, rhythmic dance of supercontinents, the story of how the planet learned to recycle stone is the story of Earth itself. This is a narrative of constant transformation, where destruction and creation are two sides of the same coin, driven by the relentless engine of plate tectonics. This recycling system has built our mountains, shaped our climate, and may have even cradled the first life in the chemical-rich waters of hydrothermal vents. It reminds us that the ground beneath our feet is not a static stage but a dynamic, living participant in an epic that spans billions of years. The ancient philosopher Heraclitus observed that the only constant is change, and nowhere is this wisdom more profoundly etched into reality than in the geological saga of our world. We are temporary witnesses to this grand, billion-year-old process, a fleeting moment in the planet's long memory. If this journey through deep time has changed your perspective on the world beneath you, share your thoughts in the comments below and subscribe for more explorations into the hidden mysteries of our planet.